So thank you very much to the organizers for having this nice conference. So what I'm going to be talking about is a little bit less directly confinement focused than the talks so far this week. And so because of that, I'm going to try and make it quite pedagogical. And so what I'm going to try and do is give kind of an overview or a review of QCD observables in collider physics that people can measure, focusing in particular on this energy correlator observable, which is under good theoretical control. And so in particular, what I'm going to try and do is to make this quite pedagogical and just give an overview of what one can measure, what one can predict, and because this is kind of confinement focused, emphasize a little bit how confinement plays a role and how the measurement of these observables can help to shed better light on confinement. And so this is based on a number of works with Huajing Zhu, as well as what I'll discuss here today in particular is with two of his students, Yibei Li and Hao Chen, and as well as with Lance Dixon. Okay, so first for the very big picture, so what we're trying to describe is when we have collisions, for example, at the LHC, we're colliding things at some energy, which I'll always call Q, where Q is much, much bigger than kind of the mass or the gap in your theory. And so this can be either a CFT or something like QCD, where this is very high and these are like pion masses. And so because of that, what you get out are many, many, many particles coming into your detectors. So this is very different than like an exclusive scattering amplitude. So you get, for example, hundreds and hundreds of particles coming out. And so this may look, if you've seen pictures of LHC collisions, kind of schematically like this. And so what you'd like to do is to be able to characterize the fluxes coming out to infinity. So for example, of energy is the one I'll focus on. You can also do, for example, electromagnetic charge or other charges in your theory. And so obviously the kind of phenomenological reason we want to do this is that this is literally what's done in collider experiments. And so the kind of goals that you might have, so what do you want to be able to learn from making these measurements? So obviously if you have some particular theory in mind, what you might try and do by measuring these asymptotic fluxes at infinity is to, for example, measure the couplings of your theory. By certain properties that I'll discuss of the asymptotic fluxes. You might want to, for example, if you can produce the system at finite temperature, you might want to try and measure transport coefficients or something like this. So this can be realized in the real world by making some kind of quark-gluon plasma in here. And so you might want to measure its properties. Or if you're in this collaboration, you might want to understand, for example, the confinement process. And so as I said, the reason why we're interested in this kind of abstract question is because this can be done in the real world in experiments. And so this is a very abstract picture, which is kind of generically true in any field theory. And so now I want to kind of specialize a little bit to the case of an asymptotically free and confining theory to show how this kind of picture changes, because this will be very important in understanding the structure of what we actually see in experiments. So if I redraw this, so if I have an asymptotically free plus confining theory, then trying to understand these observables becomes much more complicated. And so the reason is that in the kind of center of my collision, if this is done at some very high scale, in the center of my collision, I'm probing my theory at the scale at some very high energy scale, where I describe things in terms of perturbative quarks and gluons. So I have kind of dynamics at the scale of some very high energy scale Q. But the problem is that the measurements you make, or not the problem, but the difficulty, is that the measurements you make are always on, so this can be thought of as kind of the UV of your theory. The measurements you make are always at asymptotic infinity, and so they're always on the hadronic states. So the measurements you actually make in your detector are on like little hadrons out here. So these are hadrons or mesons or blue balls or whatever. and these are in the deep IR. And so the difficulty in QCD is that any measurement that you make necessarily involves just the complete description of everything going from this very high scale Q all the way down to the infrared. And so in particular, it involves kind of intermediate regimes where what happens is these start to, you have some kind of RG flows where you produce many, many quarks and gluons. And then these ultimately hadronize or so just as a kind of language, so often in collider physics, people use the word hadronize, which is just the process of confinement from, let's say, gluons into the kind of glue balls or mesons that you observe in your detector. And so in between, you have some kind of RG flow between the UV and the IR. And so there's kind of, you can view this as either an upshot or a downshot. So one difficulty is that in any kind of calculation of a real-world collider observable in QCD that you make, you have to in some way deal with the fact that you're ultimately measuring hadrons. And so because of this, hadronization effects modify any observable in QCD. And so, but if you kind of flip this around, what it allows you to do is to actually kind of observe, if you're able to understand the energy flux in your colliders, it allows you to kind of observe the dynamical process of this confinement transition. So if you can measure these things precisely, it provides some insight to how the kind of quarks and gluons dynamically form into the hadrons which come into your detector. And so now one can ask kind of what are the big picture goals of what one would like to do. So just to reiterate what I kind of said. So the goals, or what I want to kind of discuss, is kind of one, how confinement manifests in these observables. And then the second is what can we hope to learn about confinement by performing these measurements. And the other thing which I think is important to kind of emphasize before going on is, so these are things that people have studied for kind of many, many, many years. And so one should ask kind of why one continues to do this, or why particular now is kind of interesting for these. Why now? And so there's two, at least for me, two primary reasons. So the one is that there's a lot of new data. And so I'll show some in a minute, which I think really kind of clarifies a lot of the kind of issues which were kind of very ambiguous in earlier data. And so this is both very high resolution and at very high energies. And so this will be very useful in particular for learning about confinement or things that we don't understand, having extremely good data. And then the second thing is that we now have much better perturbative control. And so this has come from a variety of different directions, some of which I'll talk about during this talk, from both kind of the ability to calculate scattering amplitudes better, from insights from conformal field theories, as well as from effective field theories. And so what these enable us to do is to calculate very, very, very well the perturbative pieces of this observable, and so then combined with very good data, we can actually look at the modifications due to the confinement and kind of understand these quite quantitatively. And so it's really this kind of combination of much better computational techniques with this very nice data, which allows us, or which makes it, at least for me, exciting to continue to look at these things. Okay. So now what we want to understand is what type of observable should we measure? And so of course this depends a little bit on one's taste, but the kind of thing where at least I think there's hope for really making progress is if your observable satisfies kind of two things. So the first is if you just measure some completely crazy like distribution of many, I don't know, tetraquarks going different directions, you're just never going to be able to calculate it. And so while it's interesting for looking for states, it's just not something which you can understand. And so what we want are observables which have good perturbative control, either perturbative or theoretical control. So that we can really hope to have a good understanding of how this observable behaves just in perturbation theory to be able to look for the modifications from, let's say, confinement. And so equally well, you can consider observables where you have them under control in, for example, a conformal field theory or something, so that then you can generalize it to these confining theories and understand how confinement modifies it. And the second is you want observables that are actually sensitive to the dynamics of the energy flux, or the hadronization process. So you can make extremely simple observables, which you can compute. For example, the thing that was obviously done first in QCD would be something like a total inclusive cross-section. And so this is just in the CFT language, like a two-point function. So the simplest thing you could possibly compute, and this is what goes in the name of a total cross-section, where we just have some two-point function like this. And so this, you can just imagine that I produce a bunch of stuff here. I have my cut like this. And so I don't actually measure anything. I just measure the dependence of the total cross-section on Q. And so this is something which is very well behaved in perturbation theory. So it's just some sum of numbers. It has a nice perturbative expansion in the coupling, but it doesn't really tell you very much about the actual internal dynamics. And so what one wants to do is to be able to kind of generalize this slightly and to kind of maintain the ability to compute things, but to actually learn something more about how the energy is distributed. And so the way that this was done, or a nice proposal for doing this, which dates back quite some time now, is what are referred to as energy correlators. And so this was proposed by Ellis and collaborators in the late 1970s. And they said, and so I'll first do this in a very kind of perturbative language, and then I'll kind of upgrade it to the slightly more modern language. So they said that the simplest thing one could do is to just measure, instead of it measuring the total cross-section, where you just integrate everything over the phase space, is you can put some simple weight. And so this is kind of like going up from a two-point function to some higher point function. So the simplest thing you can do is to measure the distribution of energy. And so in particular, they propose measuring a two-point distribution in the energy flux. You can obviously generalize it to higher. And so the way you should think about this is I just have some kind of fluxes coming out like this, and I want to put two detectors which measure the energy flux coming into them. So I can put one here and 1 here. And so now this will be a function of the angle between these two detectors. And so in perturbation theory, this is very simple, because what you do is you literally take your original object, which you're integrating over all the phase space, and you just weight it by some delta function. So this is E1, E2, and you weight it by the product of those times some delta function of this, which I'll call Z, minus the dot product of the momentum. And so here the Z will be, or flip between them, this relation to the angle. And so in a slightly more modern language, the way you should think about this is you can really write down, and I won't go into too much detail in this talk, but you can write down operator definitions for what these detectors are. And so this was kind of rejuvenated by Hoffman and Malacina, but it was known much earlier to, for example, Korchamsky and Sturman, is that they said you can write down nice definitions for these objects, which are called energy flow or Anneck operators, which just measure the energy flux in some particular direction. And these, in general, in a massive theory, they can be given as some integral. So what you do is you just take your stress tensor and you integrate it over all time and move it off to infinity, and you can show that the action of this on a free particle state is just to return the energy. So if you act with this on some free particle state, it just gives back the energy times some angular delta function in that direction. And so then what you're actually measuring in a more kind of field theory language, in this case, is some 4-point function, either or in some state. It's some in correlation function of these two objects. And so this object has a number of very nice properties, which make it kind of appealing for trying to understand it in real world QCD. So first of all, it's computable in perturbation theory. Yeah.
What are you integrating over here in this epsilon?
This?
Yeah.
Yeah, so this is an integral over time.
Over time.
Yeah. So if you only have massless particles, you can just put this thing at null infinity, integrate over the null coordinate. But if you have massive things, then you really have to do this kind of limiting procedure. And so you should think of it as just averaging over the energy flux that's coming off into your detector over all times. And so that's why this is kind of an expectation value of the energy flux in some particular direction. And if you act with this, you can really just write this in terms of free creation and annihilation operators and act with it on some momentum state, and you really, just because this is like A dagger A, it really just picks up and weights by the energy. And so it has a very simple action on free particle states.
And is the n vector is the direction of which I'm looking.
Exactly, yes. And so hopefully, this will hopefully become more clear in a second, So this thing is very nice because it's computable in perturbation theory. It can be studied in conformal field theories, which makes it very nice. So although the language I've used is kind of in terms of particles, once you have this definition in terms of the stress tensor, if you're given the 4-point function or some endpoint functions with stress tensors in it, you can integrate them up and get this in, for example, a strongly coupled theory. So this was done by Hoffman and Malacina. And so this provides a lot of intuition for how this observable behaves in different theories. And then finally, the nice thing about it is it can really be measured in the real world, as I'll show in a second. And so this makes it a kind of nice combination where you can kind of gain intuition for how it behaves in all these different types of theories, and then go out and actually measure it and see how it behaves in real world QCD. And so there's been a lot of recent interest in measuring this at the Large Hadron Collider. And so what this has done is to kind of rejuvenate people's interest in going back and to look at how this observable behaves in E plus E minus colliders, which are like the simplest possible case where it's really sourced by like a local operator. And so you can measure it there now extremely precisely and really kind of test all these features. And so what I want to do is just to kind of show, this will be a very experimental thing, and I want to kind of show exactly what this is showing and step through this plot in some detail.
Why this is cleaner in E plus E minus rather than proton-proton?
Well, why is it cleaner?
Yeah.
Because you're, good. So in E plus E minus, so this is, if you think about what this, so as written here, this is really just a generic state. So in E plus E minus, I really have like a local operator acting on the vacuum. And so it's really, is legitimately a 4-point function. In proton-proton, I don't have a local initial state, and so this makes it more complicated. And the other nice thing is that so it's not that you can't do it, I'll show.
Can you do it with quark, like what's colliding is the two quarks inside the protons?
Good, so you definitely, you can, but you have all this extra kind of stuff along with the protons, and so it makes it, so we can deal with that, and it's known how to, and I'll show later results for this in proton-proton. The other reason, which is very nice, is in an E plus E minus collider, I can really go to like the center mass frame, like it's really spherically symmetric, and so I can measure this over the full distribution of angles. In a proton-proton collision, because you have the boost invariance, it's more like you can only measure, so it's nice in certain collinear limits, as I'll discuss, but you can't measure the full kind of distribution. So here you can really measure it, the full kind of distribution of energy flux on the sphere in the kind of most idealized setting. So we actually started in the LHC just because there was a lot of data, and so now we've gotten people to go back and analyze it in this case, which is very clean and kind of easier to understand. And so what, yeah. What I want to now show is what this looks like in real world QCD, just to show that this is quite like a rich object, and then I'll try and give an overall sketch of the different physics going to different pieces, and then I'll go into a bit more detail about it afterwards. And so my hope is that people, since this is, it's a very experimental plot, so my hope is that people ask questions just to make sure that this part is understood before going on. So we can spend a bunch of time to try and actually understand this. And so just to, so this is, just to cite, this is done by so this reanalysis is done by the group at MIT. In particular, Yanjili, Hannah Bossi, and Yichen. And so one thing which one can see in particular, that the data is extremely, so I've lied a little bit just because I can't quite show you the data, but this is something that essentially reproduces the data, but the data is equally finely binned. And so you can see that this is now measured extremely precisely. So there is a huge, huge number of data points, and you can measure it to very, very small angles. So this is like 0.001 radians. And so you can see that this has this very rich structure, which I'll try and make a.
So it's literally this thing that's plotted, or
it's literally, so this is an exact mapping. It's literally this thing where this operator is the like psi bar gamma mu psi. So it's an exact measurement. That's why the E plus E minus is very nice. That there's no like wiggling around with other things like you have to do in PP. So this is an exact measurement of this.
there's something divided by E squared. What is it?
Good. So this is just I normalized to the total. So divided by the E squared is just the total collision energy. So this is just normalizing to like the total cross section. So you can think of it as normalizing to like the one. So really I should normalize this to the like O dagger O total cross section, which I showed before. So that's just an overall normalization. Okay.
Archived MC is Monte Carlo, is it?
So yeah, so this is because it's not published yet, so I can't show their actual, but the thing that you should take, so the data looks exactly like this, and the thing that one should take away is the kind of fineness of so the data is an equally fine binning. Okay.
What do they simulate in Monte Carlo here? It's just QD, or they do more?
So this is a full QCD simulation, which includes hadronization. And you'll see, so important. So what's so I'll explain in a second. So the fact that these turn over is the hadronization transition. And
the lower part, the ratio part, what is it?
This is just ratios to a particular Monte Carlo. So it's like the deviation in the different Monte Carlos.
Okay.
Yeah.
Yeah, sorry, the physical interpretation of the plot. Sorry, what's the y-axis? You say it's some sort of flux, energy flux, and the
So,
x-axis angle.
I'll explain this hopefully in quite some detail. So I'll try and make a big version of this plot. So on this, so what's being plotted, so it's normalized to the total cross-section, but that one can just ignore. So what's being measured is really this this 4-point function as a function of the angles between the two detectors. And so because some people are used to different variables, in here this is plotted as a function of the angle between the two detectors. And so if one is used to these z variables, it's important that there's a Jacobian which modifies the scaling. So it's just important for people that are used to being in the z variables. This is really plotted as a function of the absolute angle between the two detectors. And then this is the angle on this axis. And so the angle goes between 0 and pi. And so this is plotted to emphasize the two endpoints. It's plotted in a kind of unusual way. So you've divided the plot in two about pi minus 2. And on this side, you do a log plot in the angle. So on this side, it's in a log scale in the log of the angle. And in this side, it's done in log of pi minus the angle. So this allows you to really see the endpoint behavior in extreme detail, which is one thing which is very nice from these new measurements. And this is where the kind of effects of hadronization are important. So now what I want to do is to build up the different kind of pieces of what go into the actual calculation of this. And to do this, I'll just switch to so this will be a kind of theory thing, piecing together the theoretical description of the different piece, which I'll then draw over here. So this is the same thing with different theory things overlaid. And so the first part I'll draw is if you just compute it in perturbation theory. So if you compute it in perturbation theory, what you get, and I'll explain later why, is you get some curve which just diverges like this. And so this is really, you should think about this as like in the UV, you just do some perturbation theory in terms of your quarks and gluons, and you get some green curve which just diverges off at either end. Then unfortunately is a purple. So then, as you go towards either side, as I described, you start to get into kind of renormalization group flows where you start to get very high numbers of particles as you start transitioning to the IR. And so what happens in this side is you have to do a type of resummation, and I'll explain these again in detail later, which takes over at some particular point. And so this is this purple curve shown here. And so this is described by this light ray operator product expansion. So again, this is, for now, this should just be schematic. But I'll go through the details of these after. So it turns out there's an operator product expansion for these light ray operators when they're very close together, that you can expand them over some other set of light ray operators. And this predicts a scaling behavior for this, which is approximate, or which goes like 1 over, if I do it in terms of theta, to some particular anomalous dimension, which you can compute. But so this still diverges, as you can see in this plot.
So could you explain a very basic thing? Why, like angle pi over 2, this is a DPV thing? Is that because all momenta are hard, like there is...
Yeah, exactly. So you can think of it, and I'll hopefully explain. So whenever you have some, let's say like an angular scale, so you do the collision of some scale q. And then whenever you have some other scale in your problem which goes small, it essentially introduces other scales, in particular which are like q times theta, or q times pi minus theta. And so in the bulk of your distribution, you're really like theta's order 1, as you say, everything is really hard, it just has to go different angles, and so you can alternatively say there's no other parameter in your theory, and so all the dynamics is at the scale q. And then once you have some small angle or some large, another object which goes small, you get or dynamics at those scales. And so this is what leads to some, so like in a confining or in QCD, you're really evaluating the coupling at these scales. And so this is why you really so this is where you'll see like confinement will be, so obviously the plot you see, or in data, it turned over, and so that's because you'll have confinement at these scales where you're really like deep in the IR. And so particularly once these scales hit lambda QCD, then what you'll see is just free hadrons, so the behavior of free hadrons.
Ian, what do we know about power-like corrections at the region pi over 2? How does they behave? Because we still have lambda over q.
Good. So I will get to, so the one that I'll discuss a little bit more is, you'll see, so this purple is already a very precise, so this is like next to next to leading log, so with like 3 loop anomalous dimensions of the collinear limit. And you can see that there's a clear deviation, in particular up here from that. And so that's from power corrections due to confinement. And so, good. So that's the part I'll add next. So there's some region in the middle where you have this fixed order perturbation theory. This is like the deep UV. You then start flowing to some region where you have this light ray operator product expansion. And so if you were in a CFT, this would really just continue forever. In QCD, where you have the confinement scale, you'll then enter some regime where you have a kind of first corrections due to the structure of the presence of lambda QCD. So you can think of this as kind of doing like conformal perturbation theory with the additional scale. And so in particular, so there's an old prediction of Korczynski and Sturman, and I'll explain this later, that what actually happens is that you get a lambda over Q in power correction, which goes like 1 over theta squared in these units. And so what happens is that it gets even steeper. And so physically what's happening in this region is that this is due to, so you get this even steeper power law. And so what's happening here is it's coming from kind of breaking of string. So it's like you have some splitting, and so you have some strings which are kind of breaking apart and populating the very small angles with hadrons. So this is now very fishy, so I'm just trying to give a global picture, then we'll go through these in more detail. But so what it does is actually quite interesting, is that it enhances the scaling of the hadrons at very small angles as compared to even the perturbative growth in a CFT. So you get this region where you kind of dump hadrons inside, and then at some scale, which is exactly the scale of lambda QCD, what happens is that then you can't do these, so you could continue to expand in lambda over Q, and you get these more terms which go up, but at some point you have to just resum, and this is the full kind of confinement transition into hadrons. And so what happens is you get this sharp transition, and then you get a perfect power law scaling. And so this is exactly just a geometric scaling. So in this is a proportional theta, and this is of just free hadrons. So it's uniformly distributed hadrons.
Sorry, Ian, shouldn't it be theta 2 minus gamma 3? Why is it 1?
Or good. So this depends. This is exactly this issue.
Okay.
So at small angles, remember this. There's a so d sigma dz is like theta d theta,
I guess
and so it flips the. You have an extra. So it's like it's 1 over theta to the 1 in both. If you work, so it goes like 1 over z to the 1 minus gamma, but if you do this Jacobian, which you invert, so that's 1 over theta squared to the 1 minus gamma 3, but then in the Jacobian there's a theta. So it really depends exactly what you're plotting. And so the same as this free hadron region, right, it's like d sigma dz is like 1. And so this is tilted at all. You can think of just like essentially multiplying it by theta at small angles, which is what flips it to 1 minus gamma 3.
But importantly, it has 1 extra power of theta, this Krzyzewski's term.
Exactly. So that's the important, yeah. It has 1 extra power of theta, which is actually kind of surprising. Like it really increases it. And this is kind of from hadrons being dumped in, and then it turns over. And so the thing that's very nice in this very precise data is that you can now do very precise perturbative calculations and measure it in this whole range, and so you really see this confinement transition to the d pi r. And so just to show this, so this is in a kind of log-log plot where it doesn't look that sharp.
Sorry, can also say a few more words about this picture of uniform free hadrons. What is the picture that you have in mind?
Good. So here you can really do it with like, you could do it with like the Cairo-Lagrangian and like with just like free pions, and you just have some like source, which now just has like n. So it's actually very similar to what you did in the And so if you computed that, it's really just this. And so the problem with trying to use, for example, like your calculation, is that what's happening is you're kind of getting to this not by having just a hard source, but the multiplicity is like growing as you go through. And so it only holds, like your prediction for the final ones actually goes the wrong way on this side. So if you look at it, it goes kind of up, whereas this one turns over. And so this is because it's really like the multiplicity is being produced as you go along. And so it's something like and so on this side you can understand as just free hadron, you can calculate as just like a free theory. And then what happens in this middle region is really the full confinement transition.
But I think only Sasha understood the answer to his question.
Okay, sorry.
Not just saying that it's the same as he did, but...
Good. So you can just, what you can take in this, so you can either, like this one is a very easy, like you can really, if you just take, this is like uniform phase space. So you can really just take like a free scalar theory and just have some operator with like phi to the n and just compute the correlator on this with no interactions. And you'll get just this power law. Alternatively, if you do it like strong coupling, so this is also the power law that Malacina, it's just like a uniform, like completely uniform, like fluid or something, gives this behavior. So this is like in this z variable, it's like, so he famously got this like flat distribution, and it's just if you rewrite it in the theta coordinates as this distribution. And so it's really what you get for like a non-interacting theory. So that's like saying at very long distances, or you just have hadrons that are just like freely floating into your detector.
You're measuring your energy correlator in free theory in some states that
it's equivalent. It's equivalent to, so like in this original picture that I had of the kind of pions, where like pions coming out, like over here, it was down here. So you're really you just have a bunch, you're measuring at such small scales, you have no memory of kind of where it was produced, and you just have like, or the confinement transition is completely washed out, and so it's equivalent. So if you really had like a free scalar theory, you get this distribution for all angles. And so the thing that's different in QCD is you get this distribution only at very, very, very small angles.
That's one more question is it not how this picture will get modified at large n? For example, like string breaking would be very suppressed, right?
Yeah, good. This is a very good. So yeah, that's a very good. So I'll move this up for a second. So if you, so it's very hard to make a model that does this because you really need it to be asymptotically free here. So like string breaking is very easy, and then it confines. And so if you really, as long as if you don't have string breaking, what happens is the two things just like go off and then just like bounce back. And so it just destroys, like you can just get a flat, or depending on how it, like, in some sense you almost just get something like sitting at the, like it just bounces back to the origin. But it completely destroys this picture. And so you really, it's like essential, in particular, this scaling is really due to string breaking. And so you need like asymptotic freedom, string breaking, and then suddenly that it confines to get this turnover.
But I mean, at large n, I would still confine. So
at large n, you would just have this distribution for the entire thing, essentially. So at large n, it's easier to go in these variables, and then you just get like a distribution that's just like flat. So this is in this. And so this is like in Malacina's calculation, in like strongly coupled large n.
Wait, but there are two things, right? There are large n and large lambda, and
yeah.
I think you can take.
So you want large n, but
I want confinement scale fixed.
Yeah.
But large n, so I'm still asymptotically free. But I mean, beta function depends on the 't Hooft coupling, right? So
yeah. So I think you'd have some differences in this kind of region here. Mm-hmm. So I think this scaling is very sensitive to easily being able to break your string. So if you really had asymptotic freedom, you still have this region over here, mm-hmm. and then you presumably have this region, and it would really be, I think, the shape of this transition that would be different. And so this is why the like extraction of these parallel. So the same as like a simple way of doing this instead of confinement is just like Higgs the theory, and then you can just directly compute these turnovers. And so it also has a slightly different like structure of these. And so that's why it's kind of these power laws which are telling you something interesting about the actual dynamics of this transition.
You say in the Higgs.
In Higgs, it will still be like this here.
Just free massive.
Exactly. And then you can just analytically compute this turnover and like expand it. You get different. So there, kind of like instead of going up, it turns like down before and goes over. And so it's kind of the scaling. The thing that seems like the full thing is very hard to compute, but the thing that can be kind of reliably predicted is the scaling as you approach this confinement transition from either side.
So who has done that in the Higgs theory?
Well, this is just for like fun. We've computed, so we've done it with, you can do it with like massive quarks and stuff. It's just for like gaining intuition of.
I mean, is it in the paper?
No, it's just calculate. Yeah, but you can also do it. So like for massive quarks, it has a similar behavior, and so that's more relevant. And so that one, it like has also been measured. And you can see that for massive quarks, it behaves differently in that turnover.
For very massive quarks, how it behaves?
Good. So very massive quarks, what you should think of is instead of having this confinement transition at the scale lambda, that confinement transition occurs at the mass scale of the heavy quark. And so you can just make it like, so in the real world, you can do that for like the B quark, and that's in a regime where you have or you can perturbatively compute it. And so what happens is instead of this enhanced, you get it's actually like a negative, and it turns over just a bit faster. And so this is something that one can measure, and you really get different kind of scaling behavior as you approach this.
They are not produced up to some. So if the quarks are very massive, they are not produced, right? In all that cascade you have there.
Yeah, exactly. So what you have is kind of like one going through, and then the like radiation around it, and then you can think of it. I mean, one way of thinking like very easily what happens in this is like you just have some propagator. Like this, and so this p squared is essentially related to the angle that you're measuring, and so if your p squared is much bigger than the mass, it behaves in this kind of asymptotically free region, and then once this drops below, it just goes to some constant which is like 1 over m. And so you can, if you kind of imagine some like non-perturbative mass scale for the gluon or something, then it kind of behaves qualitatively like that. But quantitatively it's not right because it doesn't give the actual prediction for the scaling here.
So this is Q, what is so Q here when we added, what is it?
Yeah, so Q is the energy scale. So Q in this is like 91.2. So it's like the Z pole.
So could you do much higher Q when this is and see this transition electroweak theory directly?
That would, ideally yes. In practice, not yet. But so this is the highest where you can measure in these E plus E minus colliders is around this. So we'll show later in this collinear limit, you can do this at very high energy, so like a couple TeV at the LHC. And so it's not, if you had 100 TeV collider or something, you could do it in the full electroweak theory, and that'd be super cool. But like you can calculate and stuff, but just in reality you can't measure it. And so that would give like a calculable model of this transition. Yes.
If we go to this uniform free hadron picture, so there is a homogeneous distribution, and then there are two mechanisms to produce it. One is a Hoffman-Waldau like strong coupling, another large multiplicity. And the difference between the two, if you look for the first subleading ripples, in one case it does not depend on the multiplicity. Waldau in free theory it does.
Yes.
Can we test, can we see this dependence? Or?
Yes, so good. So they have also measured it as a function of multiplicity.
Yeah.
And so I can show you this afterwards, because that one they have the actual data points on it, so I can't, but I can show it to you afterwards. And so then it extends nicely this homogeneous region, and I think they're doing that more quantitatively, and then I think one can actually test a lot of these things. Yeah.
How does multiplicity come in?
Well, you imagine that if you go to extremely high multiplicity, that you would then kind of wash out the corrections and you get back to this prediction. So you kind of extend the region over which it behaves uniformly. So if I just dump in like so many hadrons, that essentially if I take like an infinite number of them, I just have like a kind of uniform distribution.
It's like the state. Multiplicity is property of the...
Of the state. So here it's a bit more subtle because it's produced through the... But you can think of it as being like producing the hard collision, a very high multiplicity thing, and then you get some little corrections to it due to the kind of fragmentation process here, but you really start with kind of a uniform overall distribution and then have like corrections to this.
Sorry, can I still ask to get it clear?
Sure, yeah.
When you talk about transition, you don't really mean a phase transition. It's simply a crossover behavior.
Yeah, it's just
a rapid change.
Yeah, it's a rapid change. Yeah, and so it would be nice to understand better how to characterize this. But this is just really as a function of this angle. You can think of you're really probing some like the way it's kind of nice to think of it as some kind of RG flow. To really like down here you have free hadrons in the deep IR, and up here you're in the UV, and you have like gluons, and so you're kind of transitioning as you go down in energy, and you have some sharp transition in the behavior, but it's not
I just wanted to make sure we are on the same page.
Yeah. No,
because we are computing this on the lattice, and we see really this very smooth behavior.
No. So this is like it's a smooth behavior. Yeah, and it's completely
Okay, just that we are on
So exactly. And so you can see it's relatively, and in particular, it's kind of like flat. Like it doesn't peak up like this, or it doesn't cusp. It's really kind of flat in this region. But just to show that it's relatively, so I'll show like it's relatively sharp. So if you kind of unlog this, you look at the kind of perturbative on one side, like it's a pretty sharp transition. But it is definitely smooth. Yes.
Could you explain why it's even symmetric across pi over 2?
It is not symmetric. It's not. And so we'll come to, so I haven't explained, it looks like in the big picture it's symmetric because in the big picture it looks kind of symmetric because in both sides you're going to the IR. And so on both ends you have this free hadron scaling. But I'll explain in a second, the actual, like the physics of this side is very, very, very different than the physics of this side. And so and so I'll get to this, well, I may not get to this, but so this is characterized by these anomalous dimensions are kind of low spin twist-2 operators. Twist-2 operate. Yes.
And what is the 3 in the bracket?
So this is it's twist-2 spin 3. And so hopefully we'll come back to this in more detail, but it's the anomalous dimension of the twist-2 spin 3 operator. And so this hopefully kind of explains, in some sense, this side of the plot. And so it's got quite a bit of physics in it, and it's kind of probing really this kind of confinement transition as you go from the UV to the IR. And so now what we can do is to go to the other side of the plot. So what happens again, so it has this, in perturbation theory, it has a behavior which now diverges like 1 over 1 minus z. So it has a kind of, at lowest order perturbation theory, a very similar power law behavior. But the actual structure what's going on this side is very different, and the physics that governs it is very different. And so what this is governed by on this side is it's governed by the physics of Wilson lines. So now I need to erase some things. I'll first write down the expression and then explain a little bit the intuition. So on this side, it's really these kind of light ray operators, or things kind of right near the boundary, or their anomalous dimensions. On this side, what happens is it's the RG flow of what you're probing of a specific Wilson line operator. So it's the and the overall, so just like on this side, you got this kind of scaling with this anomalous dimension. On this side, the structure is that it enhances to, and I'll explain this, and this is a little bit schematic, but I'll explain this maybe later. So what this is governed by is actually, so instead of this is a low spin, so it's like the twist 2 spin 3 anomalous dimension. On this it's governed by very high spin. And so in particular it's governed by the cusp anomalous dimension, which is the anomalous dimension for cusp Wilson lines, so similar to what was in Sasha's talk yesterday, just with now it's the massless cusp, or the light cusp, as well as the collinear anomalous dimension, which is the kind of subleading anomalous dimension for cusp Wilson lines. And so physically, the way that you should think about what's happening in this back-to-back limit, right? And so what this does, or if I draw the prediction, this one actually turns over because it's an exponential in perturbation theory, and so it goes like this. And so physically what's happening on this side is that you're shooting out, so if the particles are nearly back-to-back, what's happening is that you're kind of directly along the light cone, so you have like a quark being shot out in either direction, directly along the light cone. And then what happens is you only have some very soft radiation off of them, which doesn't deflect them very much. And so what you get is that these quarks, or gluons or whatever, kind of source Wilson line sources as they shoot out to infinity. And so what you're essentially measuring is the expectation value of some Wilson line. And so physically, the way you can think about it is you have your operator, which sources things here. You have your kind of stress tensor, or energy flux, which measures them out at infinity. And then you have your conjugated operator back here. So what you get is this particular shaped Wilson line, which kind of goes out to infinity and then back. And so the renormalization group evolution of this particular light ray operator, or sorry, this particular Wilson line configuration is what gives rise to this particular structure as you go this way. So it's a very different set of physics. It's kind of Wilson lines and high spin limit as opposed to the low spin limit. And the other way, which is depending on one's intuition, kind of nice to think about. So in this, you're really renormalizing these light ray operators which live at infinity. And so you're really sensitive to the physics kind of right near the boundary. Here you're kind of sensitive to, you have your kind of operator deep in the bulk, and then you have these Wilson lines which kind of go off to infinity to your stress tensor. And so you're really sensitive more to like bulk physics, as opposed to these light ray operators which are really just on the boundary. Yeah, and so hopefully this, yeah, I realize there's a lot in this, but the hope from this, and so again you get these free hadrons over here. So the hope is that this emphasizes that this is kind of a very rich object, so there's a lot of physics going into it. but also that we have quite good perturbative control over it. So you can actually compute it very precisely, and therefore you can look at the modifications due to the hadronization transition. And so this is kind of a nice, in my opinion, place for making contact between theory and these experimentally measured observables. And so this is the kind of simplest correlator you can measure. You can obviously measure like 3-point, 4-point, etc. correlators of energy flux. Or as I'll mention at the end, you can measure slightly more complicated things that involve like charges and stuff. But this is kind of the most basic object, which already contains quite a bit of information. And so what I want to do is to go into a bit more detail on different aspects of this, but I just want to make sure that this kind of big picture is kind of clear. And so before going on, if there's questions about this.
So on the right side, hadronization is not important. So really, it's calculable.
It's not calculable, but it has a much more subtle effect because the perturbative prediction already turns over. And so what it ends up doing is it does, at a very quantitative level, it has a shift, and in particular one of these anomalous, it has a kind of shift of lambda over q. But because the perturbative prediction already turns over, it's much more mild. And so the problem on this side is that the perturbative prediction doesn't turn over. And that's just saying that when you're in perturbation theory, you can just produce things all the way down to the IR, and so you just produce more and more things. And so it's a physical thing that it doesn't turn over. But then the problem is that you have no way of like turning or merging those. You really have like a problem that in perturbation theory or even any kind of expansion, this just diverges. Whereas this one, in perturbation theory, it's physically going over, because that's just saying in perturbation theory, the probability for the Wilson lines not to recoil or not to emit at all is 0. And so you're just in a much better starting point, and it's really just a little shift. But this side, you really have, and this is why, in some sense, this is a very clean probe of the hadronization structure, because you just don't get anything. You really need the confinement process to physically describe this.
Is there a similar picture if we turn on plasma in the background?
If you turn on plasma in the background, good. Yes, there is a similar picture if you turn on, yes. If you want, I can, yeah. So this is actually, it has been measured in the plasma, and it will hopefully very shortly be out. And you can see the modification of the plasma in an interesting.
Maybe one question. Not an ex. Well. So here it seemed like you were using 3 different techniques or at least 4 at least. Some light ray, then string breaking, then maybe a Carl Lagrangian or something, I don't know.
Yeah.
So is the claim about the Wilson lines is also about a different technique,
yes, it's another, it's really probing a different, this side is really probing a different physics. And so you really need, if you want to describe the full set, which is why it's kind of like a nice observable, you really go from these like low spin operators through like perturbation theory to these high spin operators on this side. And you can think of these as like different OPE channels that you're kind of organizing it in. And on this side you get these Wilson lines that you have to deal with. On this side you get these light ray operators, and you have to kind of put them all together in these different. So you can really think like you have the kind of UV here, and it's like 2 different RG flows towards these free hadrons.
Okay.
Yeah. So I don't have quite as detailed a picture for the quark-gluon plasma, but the physical, and this is where this picture of whether you're near the boundary or near the bulk makes a big difference. So the way you can think about so again, this is a very schematic. So this is my detector, and so I can imagine just like a static quark-gluon plasma to begin with. In reality, it's more complicated, and so I can imagine producing some like high energy state, which is in here, and then it splits near the boundary into my detectors. And so if I'm at very, very, very small angles, if I'm at very, very small angles, essentially what happens is that I'm really like in the light ray, fully in the light ray OPE, and so I can imagine if I just do it as a simple splitting, then my particle went like very near to the boundary before splitting. And so essentially it doesn't see the presence of the plasma. And then as I start pulling these apart, so that's why I'll have this region, which is just the hadronization region. It will turn over, and then I'll have some uniform, or this will be the light ray 1 minus gamma 3. And so I'll have some effectively unmodified scaling like here. And then as I move these apart, I essentially push this thing back into the bulk. And so what happens is there's an angle at which this splitting hits this kind of like quark-gluon plasma. And so what happens at that scale is you get an abrupt like change in the scaling behavior shown here. And so this is at essentially, so what happens is you have this at the scale like lambda QCD, and this at the scale which is like the physical size of the like QGP ball. Like this. And so then the problem is that so this is only been measured at relatively, so you can only do this with a large hadron collider, so it's not like the full circular thing. So what seems to happen is then it seems to enter some additional kind of scaling regime. So it has some like transition like that, and then it seems to go into some like slight other scaling regime, which I think there's some kind of region where it's entering, and then you get into a region where it's kind of like deep inside. And then so you imagine that then it's kind of like entirely inside the plasma. And so this is, what's been measured is kind of out to here so far. So then I don't know fully the entirety of the plot. And it'd be interesting to understand that it should also, because it's an IR effect, it will also modify coming from the other side. And I don't, yeah, so over here, question mark. But it should definitely modify like the back-to-back. It also, or you can understand a little bit, so in the back-to-back, what it does, so in the nearly back-to-back, what you can think of it is doing is it, you have like some temperature of gluons, which are kind of pushing your quark, and so it can never go as much into the exact back-to-back. Once you hit that temperature scale on the back-to-back side again, this Sudakov region turns off. And so you get again some like scaling behavior down to some angle, and then something different happens. And so there it's kind of so there's something question mark in the middle, and then on this side you'd have some modification of the Sudakov at some temperature scale of the plasma, where it would, so you'd have some like Sudakov, and then some like modified something, and then question mark. But the part that has been verified is that you do see this, like at the scale of the plasma, you see that there is an effect. Yeah. And then ideally what you want is that at this scale, you'd measure some like higher point correlation function to actually understand more than just like the scale at which things are present, but to actually understand like, yeah. And you can do this in simulations, so they have simulations like based on like n equals 4, where you get some wake, and you can like see all the structure of the wake in the higher point correlators. But that's much harder to measure, but it's like a fun thing to play with. Okay, and so is this general picture, or kind of how these probe, let's see, like the UV and the IR physics, hopefully clear. Okay, let me just check what time it is before. Okay. Yeah, good. So I will not get through everything. But I just wanted to comment a little bit more on the details of several aspects of this and how they can be measured a little bit more, or we can kind of like focus a little bit on certain aspects of this. much time, or when do I go to?
Well, you go at the pace you're planning to go, and at some point
Well,
I'll stop you, and then we'll decide what to do.
Yes, yes. Okay, I will.
Easy to talk for half an hour for sure.
Okay, good. Okay. Good. So. So now what I want to do is just, so this is just kind of a picture, make this a little bit more concrete. Some of this will be, again, just very basic, and I just want to emphasize that you can really just compute these things, they're not that crazy. So most of what we use is just perturbation theory. And so just to, so that when we compute these things, we really just have some form factor. And then we, as I said, you just put some delta function on the cut, and you can just compute these things using, for example, like a 3-particle form factor. So I just wanted to be very concrete about this kind of middle region. So if you really just do this in fixed order perturbation theory to lowest order, so this is now being done in n equals 4 by you guys to very high orders, and by Lance and Washing also to very high orders. But if you just do it to very lowest order, you kind of see the qualitative features that I've sketched in this plot, or the green part. So if you do it in n equals 4, it has this very kind of trivial answer. And so you can see, so this is the kind of this green piece shown here. And so this has, if you plot this, let's give this green thing over here. And so if you just Taylor expand this about the two ends, you find that in this, it goes like 1 over z, which is just the beginning of this power law expansion. So just if you do this, so this anomalous dimension and weak coupling, you can expand it, and so leading order is just 1 over the angle, or z. On this side, it goes like log 1 minus z over 1 minus z. And so here you can clearly see the asymmetry. So like in a plot, it looks, big picture is similar, but it's actually a different structure between the two. And then one limit, which I think would be interesting to better understand, is you can annually continue it to z to infinity, and it has very nice fall-offs. So it's like a single log behavior, and has a fast fall-off at infinity. And so this is quite a nice object, and so it's been computed to high orders in perturbation theory. So in both QCD and n equals 4.
Going to infinity implies some complex.
Yeah. So you can just take it and annually continue it, and it seems to have this nice like fall off property, which I think would be better to understand, or they constrain a lot the structure of the answer, and so it'd be interesting to understand them. And so this has been computed to high orders in both QCD and n equals 4. And they give this kind of first qualitative hint of the structure of these two behaviors. And so, of course, physically, what's happening is that this is just the fact that you have jets in QCD. So a small angle, or an n equals 4, and weak coupling. So this is like having two particles inside your jet, and so you're enhanced at small angles, and the back-to-back is when your detectors are in opposite. So this is like pi, and this is like, or approximately 0. 0. Okay. And you can see that the thing that makes this nice is that in either of these endpoints, you have some small parameter, and so that's why you can understand the structure to kind of all orders in perturbation theory as you go towards either endpoint. So in either endpoint, so you either have z much, much less than 1, or 1 minus z much, much less than 1. And so what this means is that you can use either some form of renormalization group or operator product expansion, or depending on your liking, to understand the all orders and perturbation theory structure of the leading behavior in either of these limits. So you can use, depending on your some form of OPE or an RG, to all orders in the coupling. So you can do the leading asymptotic behavior in 1 over z or 1 over 1 minus z and understand this to all orders in the coupling. And so, because of time, what I'll discuss first, because this one has been now measured at the LHC to very high accuracy, so what I want to do is to first discuss a little bit this scaling, both in a conformal theory and in a non-conformal, or when you have a beta function, and then show the actual results for this scaling. And then we'll discuss a little bit about the other, yes?
What's the bulk interpretation of this calculation? At strong coupling, maybe, I guess.
Yeah, so I'm not the expert on this, but you kind of have two of these. So what these do is create some shocks, which go into your theory. So you kind of have some shocks, and then you have some like string or something which is kind of being imaged by these shocks in the bulk. And so there's people like Sasha knows much better about these, but this is what was done in the original Hoffman and Malvicino paper. And so these are kind of dual to shock waves. And so that's why, like in n equals 4, you can actually, or as an expansion about strong coupling, you can compute the generic like k-point correlator. And so it's kind of like 1 plus some simple corrections, which are these ripples that were discussed earlier, for trying to understand whether this is like free hadrons or very strong coupling. Yeah.
In this sense, in following of Edward's question, the presence of the quark-gluon plasma would influence this calculation, as you said, right? In a region that the shock wave touches the black hole.
Yes, yeah. And so this would be interesting this is very interesting to understand more. Doing this, getting any like finite temperature, that would be very, very nice to do. Yes. Okay. So in either of these limits, you have this very nice universal scaling behavior. Okay, so this small angle limit so here what happens, as I said before, is you get this universal scaling behavior with this particular anomalous dimension here. And so I'm just going to state the result in the conformal theory and then say a little bit about how it's modified in the non-conformal theory. So in the conformal theory, you have explicitly a light ray or an operator product expansion. And again, so for time I will not go into this, but I'll just kind of state it. Between these, so you have a light ray operator product expansion. So what that says is that you can take two of these kind of detector operators and expand them over some other set of detector operators. So I can take two of these detectors and expand them over some new light ray operator shown here. So very, very schematically, I have two of these, and I can write it as a sum of some particular light ray. And sorry that I won't have time, but there's, And so this is the twist of the operator. And so the nice thing about this is that it predicts universal scaling as you bring these operators together. And so this here, what it's or it scales like the twist of the angular scaling is proportional to twist, and so the leading scaling behavior in a weakly coupled theory is the twist 2 operators. And so these are things whose anomalous dimensions are very well known, and so you can perform these calculations to very high orders and predict this scaling behavior to very high orders. So
why is it weakly coupled? Why is it important weakly coupled theory? Yeah.
Or so if this will go like 1 over. So if I really want to just truncate it to the leading scaling of being like 1 over theta squared, then I don't want objects that have an anomalous dimension of order 1. Then I could get some like twist 3 operator or something that gives the same scaling behavior in angle as the twist 2. And so if they're really like integer separated, then if I want to predict the leading scaling behavior, I just need the twist 2 operators. So I'm assuming their anomalous dimensions are all like order 1. So yeah, if you're really counting the twist as being including the anomalous, but here it's really just that I want them like the sub pieces from higher twist operators are going like 1 over theta to the 1 or lower powers. And so I don't want any mixing between these scaling behaviors.
This is the twist of local operators, the twist of time.
It's the twist of the local operators, but they've now been turned into Lagrange operators. Yeah, but you can just read this off. So this is you can really get this as the anomalous dimension of the local twist 2 operator.
So the operator itself has which twist?
Or, I mean, so here it's protected, so it has it has no anomalous dimension.
But
yeah.
the twist.
I guess twist 2.
It is twist 2.
Yeah,
it itself appears in the OP at leading order. Is that the point?
No, because it's spin 3 guys.
Yeah, so the one between these two, this will be the twist 2 spin 3 operator that appears. So in general, if you have n of these, it's the twist 2 n plus 1 operator. Yeah.
So does this generically exist in interactances? I'm confused.
It's a non-local operator. It's not a local operator. So you can always define it.
And you switch to this d sigma dz. So this is theta squared that what used to be 1 over theta in the original.
Exactly. So this is where it's very annoying of like whether you have this d sigma dz, which is like d sigma theta d theta, and so this you have to be careful. Annoying.
In this model, the theta operator with lower twist, local operator with lower twist, does play a role here or not?
No, I don't think so, because it's really the right-hand side. Maybe a better way to think about the right-hand side is the sum of already trajectories.
Yeah.
Okay.
And then you slice them at spin 3.
Yeah.
So the fact that you have some isolated.
Yeah. So here you really have, and this is where it'll be a little bit different in QCD. So here you just slice at j equals 3, and I just want some separation here that's approximately integer so that I have a good expansion. Okay.
Do we know the convergence radius of this nitro OP?
No.
Yeah, no, it definitely breaks down at the, definitely it breaks down at the other end, so it's at most 1.
Are they proved to be convergent? No.
Because you do not have, usually you prove the convergence by advocating Hilbert space picture, but here you want to have some kind of Hilbert space interpretation, codimension 2. No such exists. So it's, but say perturbatively, if you take n equal 4, it converges. So it might converge.
And in a non-conformal theory, even less is known. So yes. So the nice thing about this is that you really just need this anomalous dimension at j equals 3. So in non-CFT, the way we think about this is a little bit different. but I'll make a connection back to this, and then show a plot.
Can I ask a question? So does the energy correlate, energy operator itself appears in OPE or not?
Here, no. Yeah.
No, okay.
Yeah.
Otherwise, it's
because you just see these things at spin 3, so it's down here. Yeah. Okay. So if you're not in a CFT, so non-CFT, but one where you can, the beta function is perturbative. Here what happens is you have one complication as compared to the CFT case, which is, as I said before, is if you're measuring, if you have Z much, much less than 1, then there's 2 scales which appear. So one is that you have to measure the coupling both at this high scale of your collision and then also at the low scale. So you get it at, it's when the momentum is, or you can show the actual scale is Q root Z, which is just, or like the virtuality of the part. And so this makes things more complicated because you really have a running in the coupling as you go between these 2 scales. And so you won't just get a pure power law like you do in the conformal theory case. And so the way we like to understand these, which is ultimately in the CFT case will be equivalent to this through a kind of neat relation, is that we treat these using what are referred to as factorization theorems. Plus the renormalization group. And so the way that one should think about it is that if we want to describe the leading power asymptotics when Z is very small, you can show that what you can do is to factorize onto on-shell states of your theory in the UV. So you have some very high energy collision, which produces, so this is at the scale Q. So you can think of this as kind of like inserting a set of states. And if you're in the UV, these are really the protonic states of your theory using asymptotic freedom. And then you have some piece, which we often refer to as a jet function, which describes the kind of small angle dynamics of that individual quark-gluon, kind of fragmenting into my energy correlator. And so this is at the much lower scale. And then what I essentially have is I can write my total expression as a product of these 2, and I have some kind of RG flow which allows me to kind of move up and down like this, which is kind of how I split things into being small angle versus low angle. And if you really do this out, you can really think of like in perturbation theory is like producing your perturbative shower. And so I won't write out the full structure of this factorization theorem. I'll just kind of make it very schematic. So what you do is you integrate essentially over the energy fraction of this particle which is produced here. And you have some, and this, things appear in a very explicit way. And so the important thing is that what this does is to split the dependence onto the of the angle is only in this IR piece, whereas this piece is just the production of the single particle state at some momentum fraction x. And then so what you can do is you can derive the renormalization group evolution of these objects, which essentially reproduces for you this expression shown here. But you can easily generalize it to incorporate beta functions. And so if you do this, what you find is kind of one, or I'll just write the expression just to...
Is this where soft collinear effective theory can
This is where soft collinear theory, effective theory is useful for proving these results, as well as for expressing. So you can ask, like, what exactly is this jet function? So it's now the 2-point correlation function of this energy flow operator in some state produced by a very highly boosted quark-gluon. And so what these are really are some quarks or gluons tied to some, they're kind of the fields in soft collinear effective theory. So they're really some like quark or gluon field tied to some Wilson line. And so these are where, like, it's to kind of prove this factorization theorem that the soft collinear effective theory is very, very useful.
And theorem is what, what is that you can write answer in this way?
What is that all, yeah, good. So the theory is that the leading behavior, so it's that the leading behavior in 1 over z so any term that goes like 1 over z, so you're neglecting things that scale like 1, and so this includes 1 over z includes like delta functions. So that all terms that are captured, or all terms that scale like 1 over z to all orders of the coupling are described by this factorization theorem here, are captured by this. And the non-trivial statement of it is that this j, or the only z dependence is in this j. And so this is very nice because this is, so in the small angle limit, what this means is that I can essentially measure it, let's say in like a hadron collider, where my initial state is very complicated, and the only thing I need to change is this. So the process dependence is essentially captured by this, and then this is just the energy correlator measured in some highly boosted, let's say, quark or gluon state. And so it's saying that, like, kind of up to a number, that the nice scaling behavior is universal or independent of the process. And this is just, again, the statement, like the operator or the OPE, that the leading term is kind of independent of the state in which you produced it in. Yeah.
How do we control in this calculation power corrections which are non-perturbative, which are even more single in 1 over z? So.
Good. So those the Korchenko, those are the claims that those are included in this jet function. So non-perturbative corrections are included in this. So you'd have to be able to to do it. So what you'd have to really be able to evaluate it like non-perturbative, but the claims that they are incorporated in this. And the same is true on the this back-to-back side, that you have a factorization theorem involving this matrix element of Wilson lines. Yeah. And so the non-perturbative power corrections come from non-perturbative corrections to this matrix element of Wilson lines. And so the claims that you have captured those in your factorization for both the leading perturbative and non-perturbative pieces. And so in perturbation theory, you can really prove this, and then also to check, just like the OP, that this reproduces all the perturbative structure. You can really prove this non-perturbative, people argue. I think if you believe that the soft collinear effective theory holds non-perturbativity, which I think you kind of do, you really believe this is a non-perturbative statement. But that's,
What if we start considering something like an instanton corrections theory? Say in n equal 4, you can compute them. And
Yeah.
Where do they live?
So in some, like, I think it depends on Korchenko is computed like instrument corrections like the cusp and stuff. And so the belief is that those are just inside. I think in the back-to-back limit, this is where things are better understood, because people have studied a lot the non-perturbative structure of these Wilson line operators. And so their belief is that they're just captured inside that Wilson line operator. And you'll see, like, what happens in this case, you can, and I definitely won't get to it, but you can get the Korchenko-Sturman result by kind of taking this, and once you have this jet function, you expand it into a set of Wilson lines. And so this is how you can kind of do an OPE inside this to capture that leading correction. And so in general, this doesn't, the non-perturbative correction is in here. And for the small angle limit, you can like see this by just you typically do a further OP. So you should think about when you're setting up the effective theory, you really have something at Q, then you have something at like Q root Z, and then you have a further thing at lambda QCD.
Yeah.
And so the claim is that this J captures all of this, and then typically, what you do is you expand lambda QCD over this, you can do an OP within this to get out the leading behavior of this.
Maybe just to be sure, so I understand the practice, but like J has a very nice definition that is at some two-point function. The hard matrix element, is there a equally sharp definition or just some parts of it?
Yeah, so the hard function, there's an equally sharp definition in perturbation, because here it's really, you've used that you have an asymptotically free theory, and so you're really factorizing onto these protonic states. And so it's really, it has an equally sharp expression as a matching coefficient onto these fields in SCT.
It's a matching coefficient, right?
It's a matching coefficient, yeah. Yeah, it's you should think of it as a matching coefficient, yeah.
And what is the physical meaning of X?
X is the momentum fraction of this internal parton. So you can really think of this as like, let's say producing some gluon with some energy fraction of the original. That's like, so the actual like energy of this, the longitudinal, would be like Q times X. And so that's why you integrate over all energies of what's going through. And then the reason why this is X squared weighting here is because you're measuring this 2-point function. So you can think of this as like E squared. So it's like some moment of this. And so because I want to get to showing the plot, I'll just state one kind of difference between the conformal theory and the non-conformal theory. So in the conformal theory, you have this selection rule that only the j equals 3 result appears, or only the j equals 3 operators appear. And so when you do this in perturbation theory, what you get are essentially derivatives in J about this particular point. And so you can just see, I'll show. So the nice thing about this is that once you have an RG, you can solve this using, you can just do its renormalization group evolution and take into account the full structure of the running coupling. So this is something that's known how to do. And if you expand it out of a particular order, you make more contact with the results shown above. So the full result is just some exponential of the integrated coupling, which isn't that nice. But if you assume some kind of effective scaling for your jet function, some kind of like effective anomalous dimension, what you find is that for example, just in Yang-Mills, you find this is exactly the gamma 3, just like it is in the CFT up there. But then you get corrections. So if I do this, this is just the lowest order in the beta function. You get corrections. So this, I'll write it as like dj. But you should really think of this as some like, melon space. Evaluated at j equals 3 times the leading order correction in the beta function and so as you go to higher and higher orders, so you have like first order beta function, second order, etc., you get higher and higher derivatives of the anomalous dimension about that particular point. And so you need slightly more information in when you have running. And so presumably there should be some way of doing this kind of non-perturbative. If you have like a weak beta function, you should be able to do some just conformal perturbation theory and prove something of this form. And so the upshot of this is you can actually, so even in QCD, although it's not quite as, it's not just a pure power law scaling, it's quite close to it and just modified slightly by this beta function. And so because you typically know these anomalous dimensions analytically as a function of j, you can do these derivatives, and you can calculate these to very high perturbative orders and extract this scaling. And so just to show that this can actually be done. And so the nice thing about this is that this, because it doesn't depend, or it depends very weakly on the initial state, only through this, is that now you can do this at, for example, the Large Hadron Collider at extremely high energies, where you're kind of very, very, very perturbative, and then you can look for this nice scaling behavior. And so there's one additional subtlety. So for technical reasons, what we actually often do, so you can generically show that an endpoint function if I again go in like a CFT, then it goes like 1 over z to the 1 minus gamma n plus 1. And so what you can do is you can take the ratio of an endpoint function to a 2-point function. And what this does is it then just scales as a difference of anomalous dimensions. And so this ends up being a kind of cleaner thing to observe.
What's the definition of Z in endpoint?
So you can take it as something which characterizes the kind of overall size. So it doesn't depend on the shape, so you can do some overall scaling, like you can just parameterize it using some, like let's say the longest side, and then you have some cross ratios which determine its shape. So experimentally, you can really just use the longest size, and that's what's done experimentally. And so this is just to again show that this is possible. So this is a measurement of this ratio of the 3-point to the 2-point. And so if you take this will go like theta to the gamma 4 minus gamma 3. So it just has this nice scaling. And so you can actually measure this to extremely high energy. So this is at like 2 TeV. So where you're very, very, very perturbative. And you can see that it has this very nice scaling behavior with these like perfect exponents. And the other thing which is kind of fun is that it actually, the scaling exponent, because these anomalous dimensions are proportional to the coupling, as the coupling gets bigger, the anomalous dimensions get bigger, and so these things run faster. And so you can see that at lower energies, you have a steeper slope, and so this is just kind of asymptotic freedom. So these just get more and more and more flat. And this is now something which can be done very quantitatively, and so you can actually use this to fit for the value of the strong coupling. So this is kind of like in, I don't know, IC model, you measure the critical exponents. So here you can measure the strong coupling from this, and you can see this as a very like quantitative thing now, which has now become possible. And this is like, or these kind of CFT and all this stuff was very useful in building the intuition for this. And so you can actually get out of this an extraction of the strong coupling, which is a few % accuracy. And so the value that comes from this is, I've kind of added it to so this is like some survey of different extractions of the strong coupling. And so the value that comes from this is this kind of red line here with the uncertainty here. And so you can see that it's not quite competitive with the world, or it's in the ballpark of the kind of world best extractions of this. And this is some kind of very initial thing that was just done by CMS. And so the hope is that one can really, there's much more room to improve this, both because you're kind of now under good perturbative control. And so the hope is that you can really, if you just shrink it by a little bit, get kind of competitive with world record extractions. And so it'd be kind of fun to do that from these nice event shape observables.
And Z is the Z boson mass?
So this is so what you do is it's just a reference point where you compare to different things. So you know the beta function to, in all sense, like infinite accuracy or to very high loop. And so you just extract it at this like high scale and then run it down to compare with other things at the Z boson mass.
What is this Z3? Is it energy or 3 energy?
It's the 3 energy. So you're measuring the ratio of the 3-point correlator over the 2-point correlator.
Is this better for measuring alpha strong?
It's better for measuring alpha strong because some of these non-perturbative corrections cancel out. And so you get like what you get is this expression here. And you cancel a number of the non-perturbative corrections as well as experiment. So part of it is just like experimentally you'd like to take ratios of things. And so it's just like that's a little bit of that's just a kind of trick. But generically it's just kind of removing a lot of like normal, like often you like to just take ratios of things. And so it's just kind of, removing a bunch of stuff. And so you're measuring this particular ratio.
So maybe a naive question. So in an ideal world, you can reduce uncertainty here to 0. So alpha S is non-perturbatively absolutely clean defined. Okay. If you have a full-fledged QCD, how do you define non-perturbatively alpha S at MZ? Like what is the non-perturbative definition of this object?
I mean, so good. So you have to just relate it. So this is like, you have to relate it ultimately to some, you have to go to like a scheme and relate it to some, so this is, yeah, so this is a good, and so this comes in a lot of, for these top masses and stuff, and so this is just, yeah, you have to extract it in some scheme, and so you have some Lagrangian, and then you relate it to a particular physical observable. So it's just some parameter, so this is the same as for these like lattice extractions, right? And so you have some like Lagrangian version of some scheme, and you match some observable, and then you can extract it in that particular scheme. Yeah.
I guess I'm asking, like, if I take a QCD as a complete theory, is there a number that responds to this, or it always comes as some fuzzy concept with some uncertainty?
I think it should. So you have to do it carefully, okay. And then I think it should be a sharp. There's a sharp thing, and so you have to be. So this is where people get into a lot. There's these, and I'm not the ultimate expert, but for things like the top mass. You have to really do it. This is where at a level beyond, you have to like use these like renormalon free schemes, because otherwise you have some renormalon in this separation, and you have to make sure. And so there's actually some people have looked at adding renormalons to energy correlators, because otherwise even in the bulk of the distribution you're doing perturbation theory and this doesn't converge. And so you need to, and so you've done some OP and you need to kind of move into a renormalon free scheme. And then the claim is that it's absolutely free, like perfectly. And so this for like top mass or something, one has already hit the level where that matters. For these, and in all, so like these extractions of alpha S, you have to put in renormalons and do, and you have to get into that level when you're like, if you go a little bit more precisely than this, you have to really start worrying about this. At this level, we are not yet. We're just working in perturbation theory. So, but that's a very good, and that is needed to understand to go below like 1% or so. But right now, for us, the leading issue is this hard function here. So like producing the state in Hadron. And so this can be done better. So people have they have very high. So now all the like 2 to 3 are known from Johannes Hahn and people and Mitov and stuff. And so this can be done to much higher order than is in here, or can be done to higher order than is in here, and should really reduce it. But this one is known to is very good now because we understand this. It's more of this hard piece. And so I think for time that will end things. But hopefully,
So maybe Jan, you can say in words. Can you say in words things that you were going to tell? Just
So I'll just very quick. So I'll do like, or can I have like 3 bullets? I'll be very. So you can understand, or just bullets. So the one is, so there's been a lot of work on this back-to-back limit. And I think one thing which is very nice is there's been progress on understanding how to compute these Wilson line structures on the lattice for light-like Wilson loops. And so then one thing that's very nice is you can use these factorization theorems to have these universal pieces, and that these can then be computed on the lattice. And so then you actually start to understand some of the non-perturbative physics.
So these are space-based Wilson loops or space-time, or?
These are space-time Wilson loops, and so these are done using these like quasi-PDF type observables by matching. And so these are light-like Wilson loops.
Light-like Wilson loops. So can this approach be used to solve the Wilson loop?
Sorry.
I think we have to discuss this.
So any non-perturbative way of getting these would be great. So like, the lattice bootstrap, that would be amazing. So better understanding these can help. The second, I was going to talk a little bit about this Korchenski-Sturman power connections for hadronization. So there, what you can do as Sasha was asking is you can refactorize this object, and you can show that you kind of what you need to compute are some is a kind of 1-point function of this energy correlator in some Wilson, or again in this like Wilson loop background. And this is some non-perturbative number, so you can fix its functional form, but it has some universal non-perturbative number, and this quantifies the size of this correction, but the shape is predicted. And then the final thing is that one can extend these to, for example, measure energy on charged on quarks. So you can do this on plus or minus particles, for example, to see how the energy is correlated with electromagnetic charge. And so one of the reasons why one wants to understand this is related to kind of properties of these kind of string breaking models, that often if you have some string that when it breaks, it's breaking to plus and minus, and so you expect enhanced correlations of like plus and minus charges at small angles. And so this is something which you can use certain renormalization group techniques to compute. And you can show, for example, that in QCD, you get actually enhanced correlations. So if you take the ratio of this like E plus E minus over, you get enhanced correlations of plus minus production at very small angles. And then if you do like plus plus over the 2 point, you get suppressed. And so you can really see that you're having like enhancement of plus minus pairs at very small angles. And so the hope is what you can do is go kind of beyond just these energy flux and start measuring more properties of the final state, which tell you more and more and more details about what's going on. So you kind of start with this perturbative thing, which you understand very well, and then kind of move beyond that. And so that's kind of it.
Okay, so now we need to break for lunch, but then I suggest that because we have a free afternoon, maybe for those who are very interested, we can have like a continuation.
Sure. Yeah.
But let's fix time. Maybe before dinner we do like at 6 or so. Sasha, what?
I'm gone.
You gone anyway?
Yeah.
Okay, so then I suggest 6 o'clock. We meet here for those even more informal, those who want to hear about these 3 things, and then we'll tell us. Is that good?
Sure. Okay.